Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. We continue to discuss perturbation theory, but in this lecture I will indicate how certain simple considerations allow us to consider perturbation theory for states which are degenerate in the absence of perturbation, and then how they change due to the perturbation and so on. So let me give you the title of today's lecture as Degenerate State Perturbation Theory. It is of course time independent Hamiltonian that we are considering. Now what if some of the states are degenerate? That is, if we have for the zero order Hamiltonian solutions which are psi n 0, let me write this E n 0 psi n 0, but then more than one state is there. The standard example is the particle in a two dimensional box. If you remember, the wave functions corresponding to the quantum numbers n1 and n2, two different quantum numbers. There are at least two wave functions which you obtain by interchanging the quantum numbers. Particle in a 2D box. If you remember, psi n1 n2 x y, the two coordinates of the particle in a box. If we assume the square box, then things are simpler. 2 by L sine n1 pi x by L, the coordinate x and the quantum number n1 appear associated, and sine n2 pi y by L, the coordinate y and n2 appear associated together. And of course this is different from the state psi n2 n1 x comma y, which is given by the function 2 by L sine n2 pi x by L sine n1 pi y by L. If we stick to the convention that the first quantum number refers to the first coordinate, the second quantum number refers to the second coordinate, but both of these states have the same energy, that E n1 n2 is equal to E n2 n1, which is given by h square by 8 m L square, where L is the side, the box length or the side of the square, n1 square plus n2 square. Okay. So we have at least a twofold degeneracy. To begin with, it can be more than twofold depending on the total energy, but the point is that it is more than one. In the case of hydrogen atom also you had a similar problem solved, namely the quantum number n l, quantum numbers n l m corresponding to the coordinates the radial and the angular. If n were 2, one may recall that L would have been 0 or 1, and for L equal to 0, m is equal to 0 is one eigenfunction 2 0 0, and then you have 1 1 1 0 1 minus 1. So the degeneracy for the hydrogen atom with the principal quantum number n is n square, 4 of them, and you probably recall that when it was 3 it is 9 SPD and SPDF and so on. So the point is there are states which are degenerate, all of which have the same energy minus Hc Rydberg constant divided by n square. So you have more than one state which are degenerate. Now perturbation theory needs to be slightly adjusted in order to account for the degeneracy, because a blind substitution of such degeneracies cannot be put in this expression, cannot be made in this expression, sorry, En2, a blind substitution cannot be made here in this part, it is going to get you into trouble. So we need to do a modification, and it is a very simple modification in principle, but which has its consequences. Okay. So the simple modification that needs to be done is in the proposal for our wave function psi n, which we wrote as psi n0 plus a lambda correction to first order. Okay. If you recall, the correction to the first order was k not equal to n, as I said, a n k psi k0. Now here, if the state n corresponds to degeneracies, then please remember that any linear combination of degenerate wave functions is also an eigenfunction of the 0 order Hamiltonian. So let me write that in statement. So we have H0, so let me use the notation that I am using, okay. Psi, so we will start with the two wave functions psi notation we have to worry about, okay, n 1 0 as E n 0 psi n 1 or n a, whatever it is. The fact is that there are two wave functions that we will assume correspond to the degenerate states, that there are two states which are degenerate, n1 and n2, both of which have the same energy E n0 psi n20. Okay. My text, written text may have a slightly different notation, but you can make the correspondence straight away by following this argument. Okay. Now given this, assuming twofold degeneracy, how do we proceed? If we know that answer, it can be generalized to n-fold degeneracy or n square fold degeneracy, as you see in the case of hydrogen atom and so on. Okay. But the point is, this is the simplest problem in which two states which are degenerate, now perturbed by the Hamiltonian H psi n is equal to E n psi n, where the H is H naught plus lambda H1 with lambda taken to 1 at the end of the calculation. Okay. So this is the question that we pose, and we want to find out what are the corrections E n, namely lambda E n 1, but and so on, but we will only worry about E n 1 for the moment, okay, for states which are degenerate. I hope the problem is clear. Now in order to understand the solution to this problem, one must note that H naught acting on any linear combination of the two states, the 0 order states psi n1 0 and psi n2 0 is equal to E n 0 times the same linear combination. It's easy to see that. Okay. So let me write H naught C1 psi n1 0 plus C2 psi n2 0. C's are arbitrary constants is equal to, just making use of the previous statement that these are states with the energy En, you will see that it is C1 H naught acting on psi n 1 0 plus C2 H naught acting on psi n 2 0, both of which give you the same answers, namely this gives you En 0 times the wave function, this also gives you En 0 times the wave function. Therefore, if you take that out as a common factor, you see immediately that the linear combination is also an eigenfunction of the 0 order Hamiltonian. Psi n 2 0. This is the only fact that we need to make use of in redefining our corrected wave function, the psi n, the first order or second order or whatever that we need to make use of this fact that there are two undefined arbitrary linear constants that we will introduce and which will have to be carried through in the algebra for solving the equation H psi n is equal to En psi n. What is the nature of these degenerate states? They are orthogonal, and if they are they are normalized, and if they are not orthogonal they can be orthogonalized. The two examples I gave you, the particle in a 2D box and the hydrogen atom, in which you have, when n is equal to 2, you have 4 wave functions, they are naturally orthogonal. Therefore, the integrals, the wave functions satisfy these property, namely psi n 1 0 star psi n 1 0 d tau is 1, and also for psi n 2 0 star psi n 2 0, they are both normalized, and the case that we have been dealing with so far, they are also orthogonal, namely psi n 1 0 star psi n 2 0 d tau is 0. If it is not, it is possible to orthogonalize them and then take that particular orthogonal wave functions as our starting point, then any linear combination of those two will also be an eigenfunction. You have realized that. Now, assuming that this is valid, all that we need to do in order to do perturbation theory is to propose our wave function, which we do not know, as the arbitrary 0 order state C1 psi n 1 0 plus C2 psi n 2 0, and nothing else changes, lambda sum over k not equal to n, this n, that n corresponds to the energy and the quantum number n associated with the degeneracy, and then all the rest of it is the same, namely a coefficient a n k psi k 0. Okay. So the only change that we make is in the definition of the wave function, and if you want to compare this with the non-degenerate case, let me just move up. Compare this with the non-degenerate state. In the non-degenerate case, you just had the non-degenerate 0 order wave function. In the degenerate case, now you have the arbitrary linear combinations C1 and C2. Now, what are C1 and C2? We will determine that as we go along and as we do the corrections to the first order, to the first order in perturbation, we will also find out C1 and C2. Therefore, the process of dealing with degenerate states is to correct for the degeneracy by taking the linear combination of all states which are degenerate as your 0 order correction and then proceeding with the first and second order. What about degeneracies in here? Suppose there are many different states, k is equal to say some other k1, k2, some other sets, does not matter, they will all be included here, but the only thing is that none of those states will have the same energy as the nth state psi n. Therefore, all states which have the same energy En0 are put together in this, they are lumped in the quantity before doing the corrections to lambda, and of course you can also do a lambda square correction if you wish by putting in k not equal to n, another quantity. Now it is instead of a, it is some other coefficient set b and k psi k0 and so on. Anyway, we will not worry about the corrections to second order and so on, but this is the wave function that we need to make use of. Okay. It is an extremely important step that, and that is the only step that we need, the rest of it is algebra. So if you need to pause here, take a short break if you wish and then come back and we will start doing the algebra in a sequence and arrive at what is known as a 2 by 2 matrix solution to the wave functions and see how the degeneracy is removed by the presence of the perturbation. Okay. So we shall substitute our proposal for the wave function in the solution, namely h naught plus lambda h1, okay, in the wave function, namely c1 psi n1 0 plus c2 psi n2 0 plus sum over k to order lambda a n k psi k 0 plus as E n 0 plus E lambda times E n 1 plus etc. on the same wave function C1 psi n 1 0 plus C2 psi n 2 0 plus lambda times sum over k a n k 0 psi k 0 plus and so on. So you know, if you collect the coefficients to lambda to the power 0, lambda, lambda square, etc. You remember the way you did that in the perturbation theory 2 lectures ago. The first term will be the statement that we made already, namely h naught acting on this linear combination gives you E n 0 on the linear combination. Of course, we already know that. Therefore, to order lambda, if we collect the coefficients, then what you have is sum over k a n k h naught acting on psi k 0, okay, that is plus to order lambda h1 acting on some acting on these two terms, namely let us not use the summation index, I will just write them explicitly, h1 c1 psi n1 0 plus c2 c1 c2 psi n2 0, that is the right hand side, that is the left hand side, and on the right hand side what you have is the corresponding term for the lambda, namely E n 0 sum over k a n k psi k 0 plus E n 1 c1 psi n 1 0 plus c2 psi n 2 0. I have just collected the coefficients corresponding to the power lambda on both sides. Again the same treatment that we have, namely we want to find out the E n 1, our objective is to determine the En1, the first order correction. Okay. Therefore, we want to manipulate this equation, and the usual method of multiplying this with a wave function, 0 order wave function on the left hand side, and then doing the integration. Except that now we have two wave functions which are in the 0th order, same eigenvalue, namely psi n1 0 and psi n2 0. So let us do two steps. One, multiply the equation by psi n1 0 and integrate over all coordinates over the entire space. The second step would be multiply the equation by the other quantity psi n2 0 and integrate over the entire space. Okay. So we do it in two steps, and it is easy to see what will happen. Okay. I am going to tell you without writing things down, I am going to tell you here. Please remember, H naught on psi k 0 gives you E k 0 times psi k 0, but this wave function is k not equal to n. Therefore, if I multiply on the left hand side by the n1 or n2, both of which correspond to a different energy, 0 order energy, and I integrate, this term will vanish. Orthogonality of the two wave functions corresponding to different energies will wipe the term out. Therefore, the term, the integral psi n1 0 star, okay, well I should put a 0 star here if you wish, and the term is H naught psi k 0 d tau goes to 0. Okay, because E n 0 is not equal to E k 0, all the other states which are not connected to that. Okay. The second term in this expression, the second term is this. The perturbing Hamiltonian H1 on psi n1 0 may give you psi n1 0 or something else. We have to actually know H1, we have to know the wave functions in order to, therefore this is not a simple statement. So what you have is, when you multiply on the left hand side by psi n 0, psi n1 0, you get two terms, namely integral psi, well let me write this in the bracket notation, okay, psi n1 0 H1, that is the coefficient C1, and psi n1 0 plus C2, the coefficient psi n1 0 H1 psi n2 0. That will be the quantity on the left hand side when you do this, multiply the equation by psi n 0 and integrate over the entire space. Please see that this is the green term, which when you multiply on the left with that, this is what you get. What do you get on the right hand side? Again, it is very clear that the first term on the right hand side, namely this one, En 0, An k psi k 0, when it is multiplied with psi n1 0 star and integrated, I mean you are taking the scalar product of two wave functions corresponding to two different eigenvalues, therefore that is 0. The second, if you look at this term, we have already said that psi n1 and psi n2 are orthogonal to each other, and therefore this will also go away when you do the integration, multiply and integrate. So what is left over is only one term, and this will give you a normalized psi n 0 star psi n1 0 star psi n1 0 d tau. It will be 1. So the answer on the right hand side will be simply C1 E n 0, okay, E n 1, I am sorry, E n 1, E n 1, okay. Now one of the things that we normally do is to write this by a notation as a matrix element of H1 between the two wave functions, and I will call this H1 1 1 and H1 1 2 for the nth state, okay. So H1 1 1 is psi n1 0, H1 psi n1 0, and likewise H1 1 2 is psi n1 0, H1 psi n2 0, okay. So the equation that we have is C1 H11 plus C2 H12 is equal to E n1 C1, okay. This is for doing this. First step, multiply the lambda term, coefficient term with psi n1. Now without repeating it, I would leave it to you to verify that when you do this with the psi n2 star 0 star, this one, that the equation that you will get, verify it yourself, is C1 H21 plus C2 H22 is equal to En1 C2, where H21 is psi n2 0, H1 psi n1 0, and H22 is psi n2 0, H1 psi n2 0. Okay. So we have a pair of equations that we need to solve in order to obtain the first order correction En1, En1, and this looks very familiar to you now because these are arbitrary coefficients, the linear combination coefficients that you have here, C1, C1, C2, C2, C1, C2. So you can see immediately that if you bring it to the left hand side, you have a pair of homogeneous linear equations in C1 and C2, namely H11, what did I do? Sorry, we used a superscript 1, so we will use the superscript 1 superscript. This is for the perturbing Hamiltonian, so that is important. So H11 minus En1, H121, H211, H22 minus En1, C1, C2 is equal to 0. So now you can see immediately that this is nothing but the eigenvalue equation for the matrix of H1 in the pair of degenerate states, psi n1 of 0 and psi n2 of 0. You can see that that is what these things are. That is a Hamiltonian, sorry, H1 2 2, that is a Hamiltonian, and that Hamiltonian is what you see here is the matrix of the Hamiltonian in those two eigenstates which are degenerate, and the eigenvalue of that matrix happens to be the first order correction to the energy. Okay. So the immediate answer is that the determinant of this is 0, namely determinant of this matrix is 0, and the determinant, if you want to write it, it is H111 minus En1 times H122 minus En1 minus H121 H211. The Hamiltonian is the Hermitian quantity, and if these wave functions are real and if the matrix element of the Hamiltonian is obviously real, then you know that Hermitian matrix implies that H121 is equal to H211. Okay. Therefore, you are left with the eigenvalue equation for En1. En1, okay, which is given by En1 squared minus, okay, En1 times H111 plus H221 is just the algebraic equation. Then you have plus H111 H122 minus, you have this quantity, namely this one H112 square, okay, is equal to 0. So this is ax square plus bx plus c is equal to 0. So you know the x is equal to minus b plus or minus square root of that a is b minus, yeah, b plus or minus square root of b square minus 4ac. That discriminant formula you can write. So if you write this, therefore the solution En1 is minus b, and this is the b, this will be H111 plus H122 by 2 plus or minus square root of b square by 4ac. So there is a 1 over 2, and b square is H11 plus H122 whole square minus 4. This is the c, this is a is equal to 1, so it is 8, whatever it is. You have H111 H221 minus H121 whole square, the square root. Okay, this is the solution to the En1, and you have obviously two solutions which you can simplify further. H111 plus H221 by 2 plus or minus 1 by 2 square root. You can take this in here to write this as H111 minus H221 whole square plus 4 H121 square. Okay. So you have two eigenvalues given by the plus and the minus, and if the perturbation was not there, the two eigenvalues would have been, because this is 0, H112, you see the correction, how it appears? It appears as that inside the square root. So you see that if this were 0, then your original solution is in the absence of perturbation. Of course the energy levels do not change, but in the presence of perturbation, the degenerate levels, both of which have the same energy En0, now get corrected by the energies, namely En0 plus or minus. When we set lambda is equal to 1, it is En1, and for this there are two solutions. Okay. And the two solutions essentially mean if the levels were degenerate, then the positive quantity adds a positive correction to that, and the negative quantity adds a negative correction to that, so that the degeneracy gets split. Okay. Okay. So this will be the E plus, if you have to write this as En plus or minus to first order correction, because we are only doing first order here to order lambda. You can see that this is En plus and this is En minus. The corrections are such that the sum of the two energies will still give you exactly twice this. Okay. So they are split symmetrically about the degenerate level. Okay. So this is the wave function, this is the energy. What about the wave function? Now we have the matrix H11 minus En1, H121, H121, H22 minus En1. This multiplied by C1 C2 is equal to 0. That was the solution that we were just now discussing, and therefore if we know these two things from that the square root factor, then there are two sets of equations, one with one value of En1 for C1 and C2, another with another value of En1 for C1 and C2. Therefore we get two sets of C1 and C2. Therefore what we get is the eigenvector corresponding to this perturbing Hamiltonian expressed in the pair of degenerate states. As a matrix, its eigenvalues are the two energies En1, its eigenvectors are the two coefficients C1 prime, C2 prime, C1 double prime, C2 double prime, whatever it is, two sets, and therefore you also have the wave function now psi n with precise values for C1. Of course this is a homogeneous equation, so you will not know C1 and C2 individually, but you will know the ratios C1 by C2. So you will still get, when you normalize this to C1 psi n1 0 plus C2 psi n2 0, you will get to know these two things, and of course you do not know the other terms, namely lambda sum over k not equal to n, whatever that is, but you remember that is a first order correction to the wave function. We never needed it to determine the first order correction to the energy. Now first order correction to the energy fixes these coefficients C1 and C2 precisely as the eigenvector coefficients, the elements of the eigenvector for the solution of this matrix. Okay, for the solution of this matrix problem. Okay, therefore that is all that one needs to do in order to correct for the effect of the degenerate states in the presence of a perturbation, and this is to first order. Now what if not two states are degenerate, but more than two states are degenerate, as in the case of say hydrogen atom, when you take n is equal to 2, please remember for n is equal to 2, case of hydrogen atom, 4 wave functions are degenerate, namely psi 2s orbital, which is given by the quantum numbers 2 0 0, psi 2p z orbital, which is psi 2 1 0, and if we write psi 2p plus, which is psi 2 1 1, it is a complex function, it is not the 2px or 2py. 2px and 2py are linear combinations of these two orbitals psi 2p plus and 2p minus, which is given by the quantum number psi 2 1 minus 1. There are 4 states, all of which have the same energy, namely H naught, the hydrogen atom Hamiltonian, on psi 2 L m. It does not matter which L and L m is, that is 0 0 1 0 1 1 1 minus 1. All of these have the same energy minus, sorry, if you remember the Rydberg constant, minus Hc Rydberg constant by 4 times psi 2 L m. Therefore you have 4 states, 4 degenerate states. So all that you need to do is, instead of taking an arbitrary linear combination of 2 degenerate states that you started with in the previous problem, here we have to take an arbitrary linear combination of all the 4 degenerate states as the necessary 0 order wave function. That is, we need to write psi n as C1 psi 2s plus C2 psi 2pz plus C3 psi 2p plus C4 psi 2p minus plus all the other wave functions to order lambda k not equal to 2, because n is 2 here. Okay, we can even put that in explicitly by saying this is the second wave function that we are looking at, psi 2, okay, and k not equal to 2, you can now write a 2k psi k 0, where this can be 1s orbital, this can be 3s orbital, 3p orbital, 3d, 3f, 4s, 4p, 4d, all the combinations in which k is not equal to 2 can be put in as a correction to order lambda, and one can obtain the wave function psi 2, and therefore the only thing that changes is the fact that you have a linear combination of 4 orbitals. How does that change the answer that you have to get? It is also very straightforward to see now that the perturbation matrix element that you have to obtain, the perturbation matrix for En1 will now contain, if you write these as n1, n2, sorry it is n is 2 now, okay, we have a notation to worry about. So if we write these, the matrix will be H1 1 1 minus E2 correction to order lambda, the first order, H1 2 1, H1 3 of 1, H1 4 of 1, and H1 2, H2 2 minus E2 of 1, H2 3 1 1. This is for perturbing Hamiltonian, H1 2 4, H1 3 of 1, H2 3 of 1, H3 3 of 1 minus E 2 of 1, H3 4, H1 1 4, H1 2 4, H1 3 4, and H1 4 4 minus E 2 of 1, the 4 coefficients that we do not know, C1, C2, C3, C4, and this is equal to 1. Now you can remember that in this case whatever we call as Hij is essentially psi I H1 psi j, where psi I is from any one of these psi 2p 0 to order 0, okay, psi 2p, psi 2s, start with 2s, psi 2p z, psi 2p plus, psi 2p minus, and this is the perturbing Hamiltonian, such as the Hamiltonian, the hydrogen atom placed in a magnetic field or placed in an electric field has this additional interaction due to the magnetic or the electric terms, and so that can be a perturbation, and to order lambda or to a very low order of the field, external field, you see that the correction that one has to calculate depends on calculating the matrix elements of the perturbing Hamiltonian in the 0 order wave functions which are degenerate, and then substituting them in a Hamiltonian matrix which is 4 dimensional now, 4 by 4, because the basis functions are 4-fold degenerate. If you are talking about the corrections to n equal to 3 in the case of hydrogen, there are 9 basis functions because it is n square degeneracy, and the matrix that one has to solve is in a very simple extension to what I have said. The matrix will be a 9 by 9 matrix, and there will be 9 eigenvalues and 9 eigenvectors, some of which may be 0, the others may not be 0, and so on, but one has to look at the symmetry of the problem more to simplify that further. But the essential point when you have degenerate energy levels, and when you want to do perturbation theory time independent for a correction term in the Hamiltonian such as H1 is that one has to set up the matrix elements of the Hamiltonian, the perturbing Hamiltonian in the 0 order states which are degenerate and solve for the eigenvalues and eigenvectors of that to get the first order corrections to the energy and the correct 0 order wave functions. We will not do the second order, third order etc. in this case, but the extension is rather straightforward, and if you have to do that it is only a question of substituting these things and proceeding the same way that you did before. Okay. Therefore, it is an extremely important extension to the time independent non-degenerate state perturbation theory, and in this one lecture I hope to have captured the minimal essential changes that one has to make in correcting to the first order the energy levels and the splitting of the degenerate energies into 2 independent or 4 independent. In the case of hydrogen it may not be all the 4 energy levels, all the degeneracy fourfold will not be completely removed or whatever, but it does not matter, the degeneracy will in any case be lifted because some of the eigenvalues for E21 will not be 0, and therefore there are corrections. One has to work that out. In a problem section I will independently deal with the hydrogen atom as one example in the future. Okay. Until then, thank you very much.